This is a video to review Chapter 8 in an Algebra 1 class, which in this case is covering exponent rules and scientific notation. So here we go. This first section, which has a lot of problems, the only instructions you have are simplify and that your answer should contain only positive exponents. So we're given things that have more than one number, have more than one variable, or a variable that appears more than once, and we're being asked to simplify, which implies that at the end of this we want only one number and then only one of each letter. So on number 1, we treat these differently, this 2 in front and this 2 in front. Then we treat the r to the negative fourth and the r squared. These 2's in front, we're multiplying together. 2 times 2 gives us 4. But when we do r to the negative fourth times r squared, there is a rule that helps us with that that says if I multiply two things with like bases, that I add the exponents. So if I add negative 4 and 2 together, I get negative 2. And so this would be my answer, except in math we have this thing where we want positive exponents. So what we do with a negative exponent to turn it to positive is we move it down to the bottom of our fraction, or if it was on the bottom of our fraction, we'd move it up. And the act of us doing that makes it change from a negative exponent to a positive exponent. Notice that I didn't write a negative anywhere here. The negative goes away simply because I moved the r down to the bottom, because a negative exponent is telling us that what we have is really a fraction, and it's not actually telling us anything about whether our problem is positive or negative overall. So our answer on number 1 is 4 over r squared. On number 2, something fairly similar happens, except this one has more going on. We've got a 4, a 3, and a 3 that don't have exponents, so we can multiply those all together in any order we want, but we should come up with 36. And then everything else we have are x's, so we're going to add their exponents together. We want to add negative 3 with negative 1, and we want to add that with 4. What that gives us is 0. So if this is 36x to the 0, there's a rule for anything to the 0 power that says that that's equal to 1. So what I really have here is 36 times 1, which is simply 36. Anytime in these problems, if we have a variable or a number to the 0 power, we can basically just make it go away and say that it's 1. Number 3 has to do with a different rule. This rule says if I take something and raise it to a power, that I multiply my exponents together. That's because what's happening is that we have k cubed, but we have it 4 times. And so based on our earlier rule where we add these together, if we're adding 3 together 4 times, what we're really doing is multiplication here. So the way you know that you should multiply instead of add is that there is not a k in between these two numbers, there's only a parentheses. So that's what helps us know to multiply them, or how we can remember that that's when we multiply. This is k to the 12th. One thing that we have to keep in mind here that shows up on question 4 though, is that everything inside of our parentheses needs to get the outside power. So this isn't just going to be k cubed squared, it's actually 2 squared as well. The number gets the power. If there were other letters, they would also get the power. But then k cubed to the second power becomes k to the 6th. Now, we can figure out what 2 squared is. It's 4, so this would be 4k to the 6th. Another rule is given to us on number 5 and number 6. Now we have an a on top and an a on bottom. Instead of adding their exponents together to combine them, we're going to do the opposite and subtract them. That has to do with the idea that on top we've got 4 a's, and on bottom we've got 2a's. So what we're doing is we're canceling out 2 of them, which leaves us with 2. We get that by subtracting our exponents. So this is a squared. Now sometimes when you subtract your exponents, you'll end up with a negative exponent, which means that you'll move whatever it is down to the bottom because we don't want positive exponents. Number 6. We've got 2 and we've got 4. We're going to simplify those, which gives us 1/2, just like normally when we simplify 2 over 4. K to the 4th over k to the negative 1. Well, that would give us 4 minus a negative 1 because we're subtracting our exponents. This will change to positive, so that makes that k to the 5th. That will go on top of this fraction, so I could just change this 1 and make it be k to the 5th. And so my answer is k to the 5th over 2. Or you could leave it as 1k to the 5th over 2. From here on out, our rules are going to get combined and made more complicated. So there may be more than one way to approach any of these problems. And I'm going to show you at least one way on each. And if there's a couple ways that are easy to do either way, then I might show you a couple ways. On number 7, one thing we have to deal with here is negatives in front of both of these. This is like having a negative 1 and a negative 1. And when we multiply together 2 negative 1s, we get a positive 1. And so what's happening is these negatives cancel each other out. So once we've done that, we still have x to the negative first and y squared. Since there weren't any other x's or y's, they don't change at all. What I want to do, though, is make this correct by moving the x to the negative 1 down to the bottom. The y squared doesn't need to move because it has a positive exponent. So this is y squared over x to the positive 1. And we don't need to write that the positive 1 part of that because a positive 1 exponent is understood as being there. Number 8. The only number we have is this negative 2. There aren't any other negatives, not counting what's in the exponents, because negatives in the exponent don't affect negatives that are outside of exponents. So this negative 2 is going to need to be at the beginning of our answer. Then we'll combine our x's. Remember that if it doesn't have an exponent, it really has an exponent of 1. I'm going to add these because they're being multiplied together. So that gives us x to the negative 1. I'm going to do the same thing with my y's. I've got a negative 4 and a 3 that add together to also get negative 1. So anything with a negative exponent needs to move down to the bottom, which is our x and our y, but not our 2. Our 2 is negative, but it doesn't have a negative exponent. And there's a difference there. When I move it down to the bottom, those exponents become positive. So this is negative 2 over x, y. Number 9. So we've got parentheses, and outside of our parentheses, we're raising this to the 3rd power. And what we want to pay attention to is that everything inside needs to get this cubed. So for the negative 2 here in front, when I cube negative 2, it becomes negative 8. When I do m to the 4th and I cube it, I get m to the 12th. And when I do n to the negative 3rd to the 3rd, I get n to the negative 9th. So I need to move just the n down to the bottom to give it a positive exponent. This is negative 8 m 12th over n to the 9th. And you'll notice that I don't try to combine m's and n's because they're not alike. They have to stay separate. 10, I want to give everything this negative 2 power. So that's 2 to the negative 2, a to the negative 6, and b to the 4th. So we've had plenty of letters to a negative exponent. What happens with 2 to the negative exponent? We're going to move it down to the bottom, and we're also going to move the a down to the bottom. When we do that, we only have b to the 4th on top. 2 to the negative 2, when I move it to the bottom, it gives it a positive exponent. When I move a to the negative 6 down to the bottom, it gives it a positive exponent. So 2 to the negative 2 is really a 4 on bottom, because 2 squared is 4, but the negative exponent causes us to move it. So this is b to the 4th over 4a to the 6th. On 11, we've got a 2 on top and a 2 on bottom. There's a few different ways of thinking about this, but most of us know that when I have 2 over 2, that I simplify that and that equals 1. So these are going to cancel each other out. Then I want to take the y's and subtract their exponents. So 1 minus negative 2 is positive 3. So this is simply y cubed. On 12, the 3 is the only regular number. U, I'm going to do 1 minus a negative 2. And v, I'm going to do 3 minus a negative 4. So I end up with 3u cubed and then v to the 7th. I can't start combining my 2's and my x's and my y's because I have to take care of the exponent first. Remember, order of operations says to take care of parentheses before anything else, so as long as there's parentheses, I can't mess with combining the x's and the y's and the 2's. When I give this all of these negative exponent, it just changes their signs. And then this is where we could go about this a couple different ways. Like, we can go ahead and move these down to the bottom and then subtract their exponents, or we could leave them alone and add our exponents. For instance, 2 to the 1st and 2 to the negative 1st. If I add their exponents, create 2 to the 0, which cancels out and becomes just 1. X cubed and x to the negative 4th gives us x to the negative 1st. Y squared and y to the negative 4th give us y to the negative 2. So x and y both need to move down to the bottom. So all that's left on top is a 1. On bottom will be x to the positive 1st and y to the positive 2nd. 14. We will give everything in here the 4th power, including the 2. That's the thing that we have a habit of forgetting, or one of our most likely mistakes. But everything gets the exponent, except the y on bottom, since the y is not in parentheses. 2 to the 4th is 16. This y on the bottom can combine with the y on top by subtracting their exponents. So this is 16 x to the 16th, y to the 7th. Let's see here. 15. Anytime we have to a 0 power, we can get rid of it and say that that's just 1. And since we're multiplying all these things together, putting a 1 there doesn't actually change anything. If I'm looking at these numbers, 4 on top and 4 on bottom can cancel. And then I want to finish off by combining my m's by subtracting their exponents. So 2 minus 4 gives me m to the negative 2 on top. Then our n squared and our n cubed combine and our n to the 5th. But they were both on bottom, so they need to stay on bottom, which means this m to the negative 2 needs to join the n on bottom. Since there was nothing left on top, we put a 1 on top. So it's 1 over m squared into the 5th. On 16, these 4's can cancel, but I still have a 2 for my answer on top. I can go about this a couple different ways. I can combine all the x's at once if I'm careful, or I can do it in steps. Like I can do x squared and x to the negative fourth together, or I can do x squared and x squared together, because those actually cancel each other out. That means I still have x to the negative fourth on top. My y's, I need to do 3 minus a negative 2, which is y to the fifth. So my x has to move down to the bottom to finish this. And this is my answer. (17). We need to take care of the parentheses pretty early on here. A negative, like a -1 for instance, to the fourth power becomes positive. Any even power makes a negative go away. So this will end up being a positive answer. And on bottom, I would change that to x to the 16th. On top, I've got a 2, and I can go ahead and combine these x's together by adding their exponents. Then I would put these together by subtracting their exponents, which gives me x to the negative 19th. So lastly, I move the x to the negative 19th to the bottom. (18). b to the 0 can go away. These two negatives can actually go together and get canceled out, because all we have is multiplication and division. So we basically just need to count our negatives, and if it's even, it means it's negative. Sorry, if it's even, it means it's positive. If it's odd, an odd number of negatives makes it negative. Or, if we hadn't done it that way, squaring those negatives would have made them go away. We also can cancel a 2 out. Just know that there's a 2 left over, which I accidentally kind of marked out with my circle. These are b to the fourths on top and bottom that can cancel. So we just have 2 left, and it still needs to be squared. Excuse me. So there's 2 approaches on a problem like this. You can simplify the inside and then worry about squaring it, or we could actually give everything inside this squared power and then simplify. I think you'll find that the first way is easier, but it just depends on which one you realize you can do first. So 18 is just 4, because everything else canceled. 19 and 20 are the end of this section, and this is about as complicated, at least for my students, as it's going to get right now. So we can do this in lots of different ways. We can go ahead and square everything on the inside here, like the negative, when I square it, will become positive. We could go ahead and do b squared and b cubed together, which is b to the 5th, and then we would need to square b to the 5th, so that's b to the 10th. This 2 needs to be squared, which is 4. Or we could leave it as 2 squared and change it to 4 in a little bit. This a doesn't have anything to interact with, so it's just a squared squared, which is a to the 4th. And on bottom, each of these needs a -1, including the 2. So here's how the 2 squared and the 2 to the -1 interact. If I left it as 4 and 2 to the -1, well, I'd move the 2 to the -1 up to the top. Or if it's 2 squared and 2 to the -1, I can subtract their exponents and get 2 cubed on top. Either way, I'm going to end up with 8 on top. So these 2's don't cancel out in some way. They actually come together to make something bigger, because this has to move to the top and get multiplied with what's already on top. Then we want to combine our a's and b's. So a to the 4th and a to the -3rd, subtract those exponents and we'll get a to the 7th. B to the 10th and b to the 1st, subtract those and get 9. So we just need to write 2 cubed as 8. Get 8 a to the 7th, b to the 9th. 20. The only regular number I have is this 2 at the top. We could go ahead and simplify this m and n with this m and n that's on the bottom. That's 3 minus 2, which is 1, and 4 minus 3, which is 1. And then everything in this needs a negative 4 for its exponent. If it's easier, think about this negative like it's a negative 1, because it's kind of weird to think about a negative having a negative 4th power. So a negative 1 having a negative power moves it to the top, which gives it a positive exponent. And so it really, all that matters still is whether it's even or odd. An even power, even if it's negative, will make this negative 1 go away, because having 4 negative 1s causes our negatives to cancel each other out. Then I just need to take care of the m's and n's. So the m to the first, m to the fourth will be m to the negative third, n to the first, and n to the negative 8. I'm minusing a negative 8, so that's n to the 9th. So the m moves down, everything else stays on the top. And that's our answer. The other thing that we tend to go over when we learn the exponent rules is scientific notation. Scientific notation is a way to represent really big or really little numbers so that they're easier to work with. And the way we know that something's in scientific notation is we see times 10 to some power. The number in front here has to be a number between 1 and 10. It can be equal to 1, it cannot be equal to 10. And so, for instance, on 21, what we're going for is 5, because we have a 5 here, and that's a number between 1 and 10. So our goal is to move the decimal to where it's on the right side of this 5. What we need to do is count how many places we moved it. 1, 2, 3, 4. So this is 5 times 10. And then we have to figure out, is this a negative exponent or a positive exponent? The way I like to think of it is that this was a small decimal number, so it is a negative exponent. And to me, that's the easiest way to do it, because otherwise we're having to think of it as being backwards, because moving to the right is not necessarily in our heads equal having a negative exponent, but that's what we want to have happen. Is small numbers give us negative exponents and big numbers give us positive exponents. So here I'm aiming for my decimal to be in between the 3 and the 7, because 3.7 is a number between 1 and 10. And so I look at where is my decimal right now. It's on the far right. I want to move it 1, 2, 3, 4, 5. And since this was a big number, 370,000, I would use a positive exponent. So this is 3.7 times 10 to the 5th. And what's happening here is 10 to the 5th is 10, or 1 with 5 zeros. And so we're literally saying 3.7 times 100,000, which is 370,000. We're just choosing to write it a different way. And we'll get to some problems here in a second that show why we would bother writing it this way if it just means the same thing. Now, going the other way, standard notation is the opposite of scientific notation. So what's happening here is we have 3.6 times 10 to the 4th. You can think of this like it's 1 with 4 zeros, and then multiply these together. Or you can say that 3.6 is really a big number because this is a positive exponent. So to make this bigger, I need to move my decimal to the right 4 places. So we need to add in zeros for these where there aren't actually any numbers. So that's 3 zeros. We have 3 zeros and then a place for the 6. So this is 36,000. 4.4 times 10 to the negative 2. Negative exponents means this should be a small number, so we want to make it smaller by going to the left. That only adds 1 0, because one of our movements is the 4. So this is 0.044 or 0.044. Now the reason why we do this is that now we can take numbers that would be really small or numbers that would be really big or a combination. We can actually work them out much quicker using our exponent rules. For instance, even though the problem is set up to make it look like we're multiplying this whole thing by this whole thing, we're allowed to do multiplication in any order. So I can choose to do 5 times 9, which is 45. And then I can choose to do 10 to the negative third and 10 to the negative second, which based on our exponent rules, we would add the exponents and get 10 to the negative fifth. Now this is not in correct scientific notation, and this part can be really tricky. I don't want it to be 45, I want it to be 4.5. So the question is, does that make my exponent here get bigger or smaller? And what it does is it does the opposite of what we think. We took 45 and we made it smaller to 4.5, so it actually adds 1 to our exponent. Negative 5 plus 1 is negative 4. We can confirm this by figuring out what 45 times 10 to the negative fifth power is as a normal number. I would have to move from where it's at right now, I'd have to move it over 5 places, which gives me 0.00045. Then if I change that back to scientific notation, 1, 2, 3, 4, I only had to move it 4 places. Okay, so that confirms that what we're saying is right. That if you have something in scientific notation that's incorrectly in scientific notation and you need to fix it, if you make it smaller, it adds 1 to the exponent, which definitely seems backward. 7 times 3 is 21. We're going to add the 3 and the negative 1, which gives us 10 squared. We want to take 21 and make it smaller to 2.1. And so that's going to add 1 to our exponent. It's going to make it go from a 2 to a 3. Now, we only had to move the decimal 1 place in both of these cases to make it the correct scientific notation. If we needed to move it more times, then we wouldn't add 1, we'd add however many we had to move it, just to clarify that. 27, the instructions on this actually were supposed to say, or might say, to round to the nearest thousandth if necessary, because 3 does not go in to 5.96 evenly. We're allowed to do this part together and then do this part together. So we need to do 5.96 divided by 3, which is 1. Put your decimal place. 3 goes into 29 9 times. Drop the 6. 3 goes into 26 8 times. I'm running out of room. So that gives me 20. 3 goes into 26 times with 2 left over, so I get 20 again. I need 4 decimal places to round to the nearest thousandth. I look at this 6 and use it to change that 6 or leave it the same depending on what it is. In this case, I round up. So my number is 1.987 times 10 to the, now we're going to subtract these exponents. Negative 3 minus 1 is negative 4. This is the only time where negative exponents are okay, by the way, is when we're using scientific notation. Then the negative exponent actually is telling us that, hey, this number is really small, as opposed to normally where we would move it down to the bottom of a fraction. 28. 1.5 divided by 3. You can do long division to figure that out. Or it might be that you can think, well, 15 divided by 3 is 5, so 1.5 divided by 3 is 0.5. Whichever way works for you. Negative 1 minus negative 3 is negative 1 plus 3, which is 2. This time, we're going from 0.5 to 5 when we fix this. We just made it bigger, and so we're going to subtract 1 from our exponent. This is because 0.5 times 10 squared we'd move the decimal to the right 2 places and get 50. And then we'd have to change it back, and we'd see that we only moved it 1 place to move it back. So you can put 5 times 10 to the first, or just 5 times 10 without an exponent, but it's not 5 times 10 to the third. We made the number bigger. So it subtracted 1. From our exponent. Or you can just change it to decimal notation and then change it back. And finally, let's raise to a power. We're giving everything in here the squared power. So 6 squared is 36. And 10 to the 4th squared is 10 to the 8th. We need to change this to 3.6. We made it smaller, so that's going to make our exponent go bigger. So 3.6 times 10 to the 9th. Here, these both need the -1 power. That should be squared. Now, 2 to the -1 is really 1/2. And 1/2 as a decimal is 0.5. So what we're getting is 0.5 times 10 squared. We need to make it bigger, just like what happened actually on 28. This is 5 times 10. We made it bigger, so we subtract 1. 5 times 10 to the first, or just 5 times 10. And that's our exponent rules and scientific notation.